Hydroboration-oxidation is an important method of converting alkenes into alcohols in a highly regioselective and stereospecific way. This reaction yields alcohols with the OH group on the less substituted carbon, and it is also a strict syn addition, resulting in both new CH and COH bonds looking in the same direction in the final molecule. In this video, we are going to talk about the details of the hydroboration mechanism and common mistakes to avoid on the test. Hi everyone, my name is Victor, and I help students excel in organic chemistry by explaining difficult topics in a clear and straightforward way. So grab a cup of coffee and notebook to work through examples with me, and let's get started. The hydroboration-oxidation, as the name suggests, is a two-step process. In the first step, we are going to react our alkene with a borane molecule. So here I have some sort of a generic alkene, and in the first step, boron, being an extremely powerful Lewis acid, is going to pull electron density from the alkene towards itself. At the very same time, our hydrogen is going to jump onto one of the carbons. This is a concerted process, meaning that the entire process happens in the same step at the same time. And because we typically classify our steps or reactions by the reagent, the boron, here being Lewis acid, means that the boron-containing compound, the borane, in this case, this species, is an electrophile, thus it is going to be an electrophilic attack on the alkene. In the course of this reaction, we are going to be at the same time making a new carbon-hydrogen bond and a new carbon-boron bond. So I will end up making a bond between this carbon and this hydrogen, and I'm going to make a bond between this carbon and this boron, giving me a product like this. Now, this step has a few important points that I want to make sure that you really remember here. First of all, this is, as I've mentioned, a syn addition. The term syn addition means that both the groups that we are adding to our molecule, in this case it is going to be my hydrogen and my boron, both of those groups end up on the same side of the molecule. They come from the same direction, they attack from the same side, same face of the molecule, which means that they will end up being cis to each other. Another important aspect of this step is that this is a concerted mechanism, which means that everything happens in one movement. There are no intermediates or nothing in between our starting materials and the products of this step. I've also mentioned that this reaction is regioselective, meaning that BH2 in this case is going to end up on the less substituted carbon, while my hydrogen is going to end up on the more substituted carbon, and we will see how exactly that looks like on the real example once we are done talking about this generic mechanism here. Two other things that I want to mention is that this reaction is typically done in the presence of THF as a solvent. THF stands for tetrahydrofuran, and that's a molecule that looks like this. THF helps to stabilize BH3. BH3 is a ridiculously strong Lewis acid, and it simply doesn't exist by itself. It is going to dimerize, polymerize, and when you have a clump of borons and hydrogens together, they're actually not that reactive. So we want to make sure that boron makes a complex with a THF rather than with itself, and this way it stays reactive. Another thing that I want to point out here is that this addition, this reaction, can happen up to 3 times depending on how bulky the alkene is, meaning that the boron atom, this guy over here, can end up connected to 3 alkyl groups, or up to 3 alkyl groups, I should say. In reality, it is typically going to be some sort of a complex system of products where boron has between 1 and 3 alkyl groups sitting on it. So for the simplicity's sake, we are going to pretend that this only happens once and move to the next step, which is going to be the oxidation part. So I'm going to pretend that these hydrogens don't really do anything for me, and they're just sitting there as a decoration. So the oxidation is typically done by the hydrogen peroxide in the presence of the base. Typically that's going to be something like sodium hydroxide or something similar to it. Usually we're going to use sodium hydroxide, or it can be potassium hydroxide or something of that sort. Now, when these two species are present in the solution with each other, there is an equilibrium, an acid-base reaction that's going to happen between them, and we are going to form Na plus with the OOH minus the peroxide anion, and we are going to have water as a co-product in this reaction. If we think about this reaction from the acid-base perspective and try to estimate the equilibrium constant of this reaction, the pKa of hydrogen peroxide is somewhere around 12. The thermodynamic value for the pKa of water is 14, which means that the equilibrium constant for this reaction can be estimated as roughly 10 to the power 14 minus 12, giving me 10 to the second power, which means that this reaction is favorable, and in the actual solution of hydrogen peroxide in sodium hydroxide, I predominantly have HOO minus rather than OH minus. And that part is important because it is HOO minus that is going to be oxidizing my molecule and attacking my boron-containing molecule from the previous step. So in my previous step, I've made this guy. And now, when I react that with OOH with a minus, the oxygen is going to go after the boron. Since boron is a very powerful Lewis acid, it's going to gladly accept those electrons from my peroxide anion, and it's going to make a species that looks like this. I have a boron with a couple of hydrogens on it with the alkyl group, and I have OOH attached to it, and now we have a formal negative charge sitting on my boron. Now, something very interesting is going to happen with this species. The electrons between carbon and boron going to migrate towards the oxygen, and the bond between my oxygens going to break, releasing OH minus into the environment. So what that's going to end up giving me is something that looks like that. The oxygen has essentially inserted itself between carbon and boron, and these electrons that I have between my carbon and boron are now these electrons between carbon and oxygen, while the electrons that I had between boron and oxygen are still there between boron and oxygen. So I kind of flip things around a little bit. Now I'm going to do the same magic trick between my boron and hydrogen, so I'm going to insert oxygens between boron and hydrogen using the same mechanistic steps. So I'm going to skip the drawing part of that and get to the product right away, which is going to look something like that. And then from this point we are already going to have a lot of OH minus floating around and pretty much no HOO minus left, usually the reaction done in such a way as to make sure that we no longer have any peroxide available by the end of this reaction. So the OH minus is going to start slowly and steadily knocking our alkoxide out of our molecule by reacting with boron. That step in reality is a little bit more complicated than that, but we don't need to go into the gory details of this exact step. We can use a shortcut which is perfectly acceptable within the scope of our course. So once I get the alkoxide like that, since we are working in aqueous conditions, I'm going to have water be a provider of my protons, giving a proton to alkoxide, which gives me my final alcohol, which is going to look like this. So during this reaction, one thing that I kind of skipped and I didn't talk about is the stereochemistry of the carbon with the boron. I first wanted to focus on the electron flow, but now let's look at the stereochemistry. So we initially started with the boron looking at me, so I will highlight that bond in red like this. This bond is still looking at me in the second step, and here is something extremely important. When oxygen inserts itself between boron and carbon, we preserve the stereochemistry. So if my boron was looking at me, then the oxygen is also going to be looking at me. So this way, by tracing my stereochemistry with the oxygen throughout this entire reaction, I can see that I replaced boron with an oxygen with the retention of configuration. And this is an extremely important point in this reaction. We are not going to racemize it, or we are not going to switch the stereochemistry. The stereochemistry of the carbon-boron bond is going to be exactly the same as the final stereochemistry of the carbon-oxygen bond. If it was looking at us, it is going to end up looking at us. If boron was looking away from us, it is going to look away from us in the final product as well. And of course, once we start dealing with real molecules, it becomes incredibly important. So let's look at the hydroboration-oxidation of my good old friend 1-methylcyclohexene here. So the first step is going to be the addition of boron to our cyclohexene. So if I quickly draw that one out, I will start by showing my cyclohexene over here, and then I know that hydrogen should end up on the more substituted carbon, while boron should end up on the less substituted carbon. So I will orient my molecule to make it a little bit easier to show the mechanism, and then double bond attacks the boron, and the hydrogen going to jump onto my carbon, which going to give me a product that looks like that. And of course, since the attack by boron can happen from the either back face, which I'm showing right now, or the front face, which will look like that, I'm going to end up with a pair of enantiomeric intermediates here, enantiomeric products of this first step. Next, I'm going to proceed with the oxidation step, so I'm going to use the shortcut right away, and instead of writing how I got my OO-, I have this OOH- guy, and I'm going to say that I'm going to attack either this boron or I'm going to attack that boron right away, giving me the following two intermediates. Then, like on the previous page, we're going to have the carbon-oxygen bond formation like this. OH is going to be released into the environment, so I'm going to only write the product for one of them for the lack of space, looking like this. And I also replaced my hydrogens with the OH groups right away, so I will show that I've used a shortcut here and combined multiple mechanistic steps together. And then finally, from this point on, the OH is going to come in, knock the boron out, give me the acid-base reaction with water, and I'm going to end up with the final product looking like this. And of course, since I'm only showing this part of the mechanism for one of the possible enantiomers, I should probably say that I have plus enantiomer over here and plus enantiomer over here as well. So here we remember that this reaction is a strict syn addition, which means that the hydrogen that I have added to my molecule and the OH group that I have added to my molecule, they are on the same side of the molecule. So they're both on the dashes in this case, and if I wanted to draw the enantiomer, they both are going to be on the wedges. However, here is something that I see a lot of students get tripped up on, and that is the fact that the hydrogen can be, well, implicit. And sometimes we are not going to show that hydrogen at all. So you can very well show your product looking like this, where you have the methyl group looking at you and the OH looking away from you. So if that was, let's say, a multiple choice exam where you have this question and you have a few different products given to you and one of the products looks like this, you might not even consider that or notice that because, well, you're seeing OH and you see the methyl group, they look like they look in the different directions. You remember that this is a syn addition, so it doesn't look like a correct product. But remember, hydrogen can be implicit, and the hydrogen is hiding right there. So don't get caught by this very common trickery on the exam. I have seen instructors pull this trick on students over and over again, and a lot of students do get caught by this trick. So remember, the hydrogen can be implicit and it can be hiding from you. Alright, how about something like that? So first step first is the addition of my boron to the double bond, making a boron containing molecule. So let's say now I'm going to end up with a molecule where my hydrogen and my boron are attacking from the front face, so they're both looking at me like that, which means that my methyl group got to be down there looking away from me. So an important thing that I want to point out here is that this carbon over here is not chiral, which means that showing a dash or a wedge on that carbon is completely unnecessary. And your instructor might very well just write this as just a simple straight line. So we can show this molecule as I still have my hydrogen over here, methyl group down there, and I will show BH2 just like that, on a single plain line. But that we can do only because that carbon is not chiral, and showing the dash or a wedge there is completely meaningless. And of course, because the boron can attack from the other side as well, this is going to give us enantiomer as well. So if I wanted to draw my enantiomer, I would only flip the stereochemistry of the atom where the hydrogen is, so I can show the hydrogen is now looking away from me, and the methyl group is on the wedge looking at me like that. So from this point, the next step is going to be my oxidation, so I'm going to react it with the HOO-, and that will replace BH2 with the OH group. So again, I'm going to skip the part of the mechanism for the simplicity's sake and for the time's sake, and just draw the final product right away, which is going to look like this, plus, of course, the corresponding enantiomer if I were to draw this product for the molecule on the right too. Now, in this case, just like in the previous case, the hydrogen atom can be implicit. So if I have the hydrogen that I am not showing there, then I can show this molecule being like this. And for the enantiomer, I'm going to have the structure looking like that, where the methyl group is now looking at me on the wedge. That is kind of a small wedge. Let's make it a little bit bigger like that. There we go. So be very careful with that hydrogen, because sometimes it will feel like the hydrogen just disappeared and the stereochemistry came from out of nowhere. But in reality, the hydrogen is there and it's making the stereochemistry in a very specific way. And of course, like in the previous case, I'm going to end up with a pair of enantiomers here. And of course, since I'm all about the exam tricks, here's the question which I would consider a tricky exam question. We need to predict the product in this reaction. So what I'm going to do, I will work through this reaction mechanistically and then come up with my final product through the a little bit of a shortcut version of the mechanism. So first thing that I'm going to do, I will add my boron across the double bond to make sure that the boron is on the less substituted carbon, which in this case is going to be, let's say, this carbon number 1, and my hydrogen is on the more substituted carbon. Let's say it's going to be this carbon number 2 over here. So once I add my boron, I'm going to end up with two variations. Variation number 1 like this, and variation number 2 looking like that. Here, like in the previous case, I have this carbon and this carbon which are not chiral, which means that I can get rid of dash and wedge on the boron and just draw those on plain lines, giving me molecules like that. I also remember that my hydrogen can be implicit, so if my hydrogen is on the wedge in the left molecule, it means that one other bond, let's say this one, gotta be on the dash. And if my hydrogen is on the dash, well, that means that that other bond is going to be on the wedge. So in other words, if I implicify my hydrogen, is that even a real word? Implicify? Implicit? Implicify? Anyways, if it is not a real word, I just coined it, you can use it, you're welcome. So I'm going to implicify this hydrogen, and if I get rid of that thing, now my molecules look like that. And then, of course, following up with my mechanism, I'm going to replace the boron with the OH, which is going to give me the two products that look like this. And what's going to be the relationship between these two? Unlike the previous two examples, these are diastereomers. So remember when I always say that you should never just do blanket statements and do the same thing for every single reaction, like say that everything is enantiomers on autopilot or anything like that? Well, that's one of those cases. These are diastereomers, so as always, be careful with your mechanisms and stereochemistry. Well, as you can see, these reactions are quite complicated, and there are quite a few cornerstone points where things can go south very quickly. And I know that I sound like a broken record saying that you gotta be careful with your reactions and think mechanistically and think about stereochemistry over and over again, but this is one of those reactions where if you are not careful with the mechanism and stereochemistry, you are definitely going to get something wrong and get tricked on the exam. So make sure you do plenty of practice and know and understand this reaction like the back of your hand. And if you got to this point with me, thank you for watching this video till the very end. I want to especially thank all Organic Chemistry Tutor members and my generous donors. I upload new videos every single day, and this would not be possible without your help and encouragement. If you learned something new today, please give this video a like and leave a comment below. This way YouTube algorithm will promote this video and show it to more people. And in the meantime, watch this video next, ask your questions in the comments below, and I will see you tomorrow.